everyone. I hope you're all healthy and well. Thank you all for joining us for the fourth talk in our Golden Week of webinars in Astrophysics series. My name is Evelyn Johnston. I'm a postdoctoral fellow at the Institute of Astrophysics at the Pontificia Universidad Católica de Chile. And together with Thomas Puzia, a member of the faculty and head of outreach, we have organized this week of webinars. We're excited to bring you talks from scientists who have significantly contributed to the fields of astronomy, astrophysics, and cosmology, and thereby expanded our understanding of the nature and inner workings of the universe. It will hopefully be an exciting and instructive journey for you, as well as for us, as we move from the largest scales of the universe over the structure and galaxy formation to the formation of planets and the fabric of reality itself. We're looking forward to bringing you these talks in the original English with simultaneous Spanish translation to your screens without any registration fees. This has been made possible by the generous support of the Vice-Rectorate for the investigation of our university, and from the Center for Astrophysics and Related Technologies, also known as CASA for the Spanish acronym. Our fourth talk this week will be given by Stephen Wolfram, the founder and CEO of Wolfram Research. But first, we'll give a brief introduction of how this webinar will run and how we can use the two languages.
We're looking forward to bringing you these talks in two languages. For this talk series, we have arranged for a simultaneous language interpretation provided by Mr. Patricio González, Director of Serendipia Soluciones, will be simultaneously translating for us both in the English-Spanish and Spanish to English directions. Our devices, on your devices, you can switch between the English and Spanish channels on the language button on the bottom of your Zoom window. So unfortunately, we've discovered that the live interpretation option is not offered for people using Zoom in the browser window or in Linux machines. So we apologize for this. And we will post, of course, both English and Spanish versions in high quality to our Astrofísica YouTube channel very soon. We also heard from a few participants that they could not mute the original soundtrack when listening to the Spanish translation. So this appears to be a bug in Zoom, and we've been told that just simply by leaving and rejoining the webinar, this should very easily fix the issue. If you have any questions during the talk, please type them in the Q&A window. To open the Q&A window, again, please click on the Q&A button at the bottom of the Zoom screen. So all viewers will be able to upvote and downvote questions and comment on them. We have a team of astronomers and journalists behind the scenes who will be monitoring these Q&A questions and select the best for discussion after the talk. Stephen's talks are a bit more freestyle and in free form. And so we have already heard this week in contrast to what we have already heard this week, so we will likely be addressing these questions throughout the talk, so please keep them coming.
I'd like to briefly introduce our panel today. So we have Stephen Wolfram, our speaker, of course, myself and Thomas, and Patricio González, who's our interpreter. From the faculty at the Institute of Astrophysics, we have Gaspar Galaz, Max Bañados, and Ezekiel Triester. And we have our postdocs Demetra De Chico, Giuseppe Dago, and Paul Eigenthaler. We also have 4 graduate students, Simon Angel, Sergio Best, Ernesto Camacho, and Enrique Paillas. And we're also very happy to invite our guest panelists today. We have Roberto Munoz, a senior data scientist at Ernst & Young and Thomas's first postdoc. We have Chris Consolis, a professor at the University of Nottingham and the lead editor at the Galaxies and Cosmology Corridor at the AAS Journals. We also have Carl Glazebrook, a professor at the Center for Astrophysics and Supercomputing at the Swinburne University of Technology in Australia, and John Blakesley, a chief scientist at Gemini Observatory. We have our usual Q&A managers, Ricardo Acevedo, Daniela Fernandez, and Carol Rojas. And in addition to that, we have Danielle Rommel, an assistant of Stephen, who is going to be helping us manage the Q&A today. Gaspar, before we continue, Gaspar would like to make a brief welcome.
Okay, thanks Evelyn and Thomas. Well, as a director, I have the opportunity to address some words of this. And well, thanks to all for connecting this webinar today. This is the 4th day of this very successful series of high-level talks. And today it's a real honor to open this 4th day. And on behalf of the Institute of Astrophysics at Universidad Católica, welcome Professor Stephen Wolfram. He's perhaps one of the most creative minds in the last 20 years in the field of mathematics, computer sciences, physics, astrophysics, business, and in fact, many areas not straightforward to define. The creation of a revolutionary new computing language, allowing a machine to manipulate and solve algebraic problems. Is it an achievement or in computer science or in mathematics? A new human language itself? Perhaps all of them. Stephen Wolfram is someone who has been extending the frontiers of knowledge in all areas, in fact. In computing and mathematics fields, he created Mathematica, an impressive program, and I have to say still a miracle for me today, that solved complex mathematics in algebraic forms by means of a symbolic manipulation program created by Stephen. In mathematics, he has extended the limit of knowledge in the field of cellular automata. He has developed frameworks and theories to join apparently separated problems in mathematics, physics, and computer sciences. When I saw the amplitude and depth of Stephen's contributions to so many areas of knowledge, I remember when I was a teenager and I was profoundly impressed by the life and achievements in mathematics and game and computer theories by Johnny von Neumann or even Alan Turing, and wonder whether someday there would be similar scientists. And in fact, I asked myself if perhaps I would have the chance to know someone like them one day. Well, I think this is such a day. Stephen, for us at the Institute of Astrophysics, it's a real privilege to have you as speaker today in this webinar series, and with, in fact, thousands of online attendees. And I'm grateful that you join us today. Thank you very much.
Great, thank you. You know, it's a really cool thing. You know, pandemics are bad, but the fact that they cause things like what you're doing today to be possible is good. So very, very nice to be with you all. So look, I thought I would talk mostly about some new developments in physics, which have been a big surprise to me and are rather exciting, and I think have implications in astrophysics and cosmology and so on. But there's also a lot to talk about computation and its role throughout science and elsewhere. And I'm happy to try and address some of those things. And I'll try and keep my comments about physics comparatively brief so that we'll be able to have a longer Q&A. But so let me launch into what we're talking about here. So, you know, back a long time ago, I used to do traditional physics, particle physics, and also cosmology. I started working on kind of the interface between particle physics and cosmology back around 1978, when that was sort of a very newfangled kind of thing to do. And so but at that time I was mostly concerned with taking sort of the existing big theories of physics, which pretty much meant quantum field theory and general relativity, and applying those theories and figuring out with great effort how to do computations that would allow us to make predictions and study the consequences of those theories. So at that time, I was not interested in sort of what's underneath general relativity, what's underneath quantum field theory. I was just interested in building on general relativity and quantum field theory. So then I kind of, by the early 1980s, I kind of started realizing that actually there were a lot of questions in science that I was asking that were not really addressable using traditional methods from places like physics. And so I sort of got into this business of trying to generalize kind of the way that we build theories to not just work in terms of sort of the traditional mathematical equations that we use for, that we've used for a long time to build theories in, for example, physics, but the more sort of general environment that we get, the more general framework that we get from using programs and as our sort of models for things in the world. And I also had been involved in doing practical things with computers, driven by my interest in doing computations in physics, actually, and I built my first computer language and so on. Anyway, so I got interested in this whole problem of sort of how do we generalize our way of making models for things in the world. And that got me involved in the question of, well, if we just look at programs out there in the computational universe of possible programs, what do they typically do? Are there interesting ones that are simple, or do you have to carefully engineer a program to make it be something relevant and interesting? What I discovered, to my great surprise, is that actually even extremely simple programs can produce extremely complicated behavior that sort of very unexpected thing. So that sort of started for me kind of a chain. Let me start sharing some things here. This should work. Okay. So the thing, let me pull something up here. Yeah, so my sort of big discovery of the 1980s was this phenomenon. So this is a very simple program. So it has just a line of cells. Each cell is either black or white, and it has a little rule down here that says, based on the color of a cell and its two neighbors, what will the color of the center cell be on the next step? Just started off from one black cell, and you get this pattern here. And so you might say, well, gosh, it's such a simple program, there must be some simple way of figuring out what this is going to do. Well, it turns out there isn't. And this is sort of part of a very general phenomenon that even though the rules for a system may be, the sort of computational rules for a system may be very simple, the behavior of the system may be extremely complicated. So this kind of observation got me started on what I think sort of turned into a whole new kind of science that's based on kind of using computation as the foundational idea for building models of things and the foundational idea for understanding how things work. And so, for example, the phenomenon of computational irreducibility that I'll talk about a bunch more later, that has to do with the question of, can you work out what will happen in the system? Well, you can work it out by just following each step, applying the rule at every cell, at every step here. But can you jump ahead? Can you make a fast prediction of what's going to happen? And the answer is you can't. This is a computationally irreducible system where sort of the only way to work out what it will do is to just sort of go through the same computational effort that it goes through. So in any case, but this sort of got me started on this idea of, could there be, what can one do with sort of simple computational rules? And so back in 2002, I published this big book called New Kind of Science that you can find online and so on, that sort of talked about this idea of using computation and simple programs as the foundation of models of things. And there were many areas where I would say rather rapidly, in fact, this became sort of the idea of using programs as models became very popular. And it's something which sort of, for me, was kind of a dramatic thing because it had been sort of a 300-year run of, if you want to make a serious model of something, use equations to, in a very short time, kind of new models that get made of things in biology and studying people on the web and studying all kinds of things, typically are made in terms of programs, not in terms of equations. But one of the areas that I sort of viewed as being a potential use case for this kind of computational view of modeling and of the world was fundamental physics. And so I got interested in the question of, could I take the intuition that I developed from things like my Rule 30 cellular automaton, that thing I just showed you, and could I apply that to fundamental physics? And in particular, could we in fact figure out that there might be some simple program, some simple rule which underlies the whole operation of our physical universe? In a sense, could we find in the computational universe of possible programs, could we find a program that represents our physical universe? And had I not seen this phenomenon where very simple rules can produce very complicated behavior, I would have thought that was just totally crazy, totally impossible to get all these amazing things we know in physics, all the sort of richness of what we see in the universe just from some simple rule. Okay, so I started thinking about this back in the early 1990s, and I thought about various things about sort of what might lie underneath space and time and so on. It's kind of inevitable when if you think there's a simple rule for the universe, that nothing that is familiar to us from existing physics will be sort of immediately in that rule. You don't get to put in a 3 for the number of dimensions of space or some particular number for the muon electron mass ratio or whatever else directly in that rule. It has to be, all of those features of the universe have to emerge from this sort of simpler underlying rule. Okay, so I started thinking about this in the early 1990s, and I kind of developed some ideas about possible models, and I got a fair distance. I could understand how, from very simple models in which I'll describe in much more detail, but how you could derive things like special relativity and general relativity. I had some vague signs of being able to derive quantum mechanics from simpler underlying models. But in the end, what I found was that in physics wasn't really ready for these things. And people were like, oh, we're happy, we're going to solve everything with string theory. Don't worry, string theory will solve it all. So about 20 years went by, and I mostly worked on kind of making computational language that allows us to have a foundation for thinking about things in the world computationally, building things that software and other things that do things in the world computationally. And that experience kind of made me all the more both convinced and interested in the possibility of using sort of computational ideas in physics. And then about, what was it, a couple of years ago now, I made sort of a little methodological breakthrough in the way that I've been thinking about making fundamental models for physics. And then a couple of young physicists came along, about a year ago now, and were saying to me, why haven't you been working on this physics project? It's such an interesting thing, you've got to pursue it, and we'll help you do it. So those people are Jonathan Gorard and Max Piskanoff. And so we started last fall trying to see whether I could use kind of the ideas that I'd had back in the 1990s and the more recent sort of tweak to those ideas to actually make a fundamental theory of physics. Okay, the really amazing thing is that it actually made huge progress, and much more progress than I ever would have expected, and much more progress, I think, and perhaps the most interesting feature of that progress is that I had expected that we kind of be building this prong of sort of development of a fundamental models of physics, very different from what had been done in sort of modern areas of mathematical physics. Turns out what actually has happened is that we did start off building a prong, but it turns out that our prong basically interacts beautifully with a lot of existing ideas in mathematical physics. And it seems to be kind of a collecting point for a lot of very abstract ideas that people have had about how physics might work, and a lot of very definite development that's been done along mathematical lines. And it sort of provides a way to sort of make the low-level machine code for the universe on top of which a lot of these mathematical ideas can sit. Okay, so that's the kind of framework. And frankly, it's been super surprising to me how well this has worked. And we're just sort of, we kind of launched this project a couple of months ago, and a lot of people have been getting involved in it. We're just about to have a summer school with lots of physicists there. We've been having a summer school about science and technology in general for about 17 years, but we added kind of a fundamental physics track this year, and got a lot of very good people coming to it. And I expect lots of interesting papers will come out of that, no doubt. All right, let's get down to business here. So what I'll do first is kind of give you a sketch of sort of the ideas about fundamental physics. Then I'll go through all of this in a bit more detail and try and explain how things work. So there are, I think, I maybe should say at the beginning, there are three things about what happens in this model that aren't what you expect from what you might know about existing physics. First thing is space is discrete. The second thing is time isn't the same kind of thing as space. And the third thing is more technical thing in quantum mechanics. The quantum amplitudes, which you think of as complex numbers, the magnitude and the phase of those complex numbers come from completely different places. So those are sort of three things that are sort of a little bit not what you expect from the traditional development of physics, although in all three of those cases, what we know about physics turns out to arise from sort of as emergent properties of this sort of low-level machine code of the model. Okay, so how do things work? So what we're starting off from is something extremely abstract, and we can describe it very abstractly, or I can kind of connect it immediately to physics. What we're dealing with is just these little rules that say we're going to have a bunch of elements. These elements are just, they're just things. You don't really have to say what they are. They will eventually be interpreted as kind of atoms of space, but at the beginning they're just abstract things. And the only thing about them is they have a definite identity. And there's one thing and it's different from another thing. That's all we have to say. Then we have relations between those things, and we can represent those relations in terms of graphs, or more specifically in terms of hypergraphs. graphs in which there aren't necessarily sort of just edges with two ends to them, but hyperedges which can have an arbitrary number of ends to them, so to speak. And so the basic idea is we're just looking at these hypergraphs, and then we say we have a rule that says, this is just one example of a rule that says, whenever we see a piece of hypergraph that looks like this, rewrite it into a piece of hypergraph that looks like this. Okay, so what's going to happen is then we're going to build up a hypergraph, and we build up this potentially very big hypergraph here, and that big hypergraph, in ways I'll try and explain, acts like space in our universe. And in this model, there is nothing in our universe except space. And all of the matter that exists is a consequence of kind of features, localized, stable features of space. Much like in condensed matter physics, for example, you might have topological excitations that represent sort of particle-like things existing in some medium. It's the same kind of thing in our model for the existence of matter in space. So first thing is, from the underlying rule, you're just applying this rule lots of times, you build up this big hypergraph. This big hypergraph acts like physical space. So the sort of one of the things to realize about this is when you build up this hypergraph, you have a bunch of events that go on. You have a bunch of rewrite rules, a bunch of applications of this rewrite rule, and you can make kind of a causal graph that represents the causal relationships between those events that happen. So one particular event, one particular piece of graph rewriting might have as its input some elements that came from another graph rewriting event. And so what you're mapping out in this causal graph is the map of all those causal relationships between different events. And so that's how you're sort of laying out space-time. You have events that can be space-like separated because they happen, and there are events that are time-like separated where they happen sort of successively, where one event depends on another. So again, talk about this in much more detail, but I just want to give you kind of an overall sketch of what happens. So we build up this causal graph that represents the relationship between events. And then the first big result is that when the underlying rewrite rule has a property that we call causal invariance, it follows that in this causal network, the causal network must obey Lorentz invariance, must show special relativity in certain limits. First result. Second result is in sort of the simplest way of setting things up, we can then show that when you look at, we can define notions of curvature and things, and we can look at what happens to JD6 in this causal graph. And the next result is we can derive the vacuum Einstein equations. Okay, so then the next thing is, okay, so what's matter and how do we understand that? So the next thing we realize is that there's sort of a bulk definition of matter where we're just talking about energy and momentum and so on for matter. And it turns out that there's an identification that essentially the density of causal edges, it turns out that the flux of causal edges through space-like hypersurfaces is energy density in these models. And so by putting that in, we can derive the full Einstein equations for our causal graphs. And in a sense, that derivation, I'll talk about it more later, but in a sense, that derivation is a little bit like the derivation of things like the Navier-Stokes equations for fluid flow from underlying molecular dynamics. And it has some of the same mathematical assumptions that have to go into that. That from sort of the discrete dynamics of these kind of atoms of space, we derive this continuum description, which is the Einstein equations with the energy momentum tensor and so on. Okay, so what about quantum mechanics? Well, it turns out in our models, quantum mechanics is not something that you bolt on. It's something you couldn't possibly avoid. It's something that has to happen in our models. And the reason is that when we think about doing these rewrites on our network, the question is, which rewrite do you do? And it turns out there's often a lot of ambiguity about which rewrite you do. And that means that you can't just build up one stream of history. There's actually a whole tree of different possible histories that are associated with different possible rewritings that could have been done. And so the sort of the skeleton of this object here represents those posits, what we call a multi-way graph, that represents all those possible rewritings, all those possible streams of history. So a critical fact, which actually is a consequence of this property of causal invariance that I mentioned earlier, is that not only is there branching of different histories, there's also merging of histories that occurs in this multi-way graph. And then it turns out that there's also, you can think about causal connections in this multi-way graph. These are causal connections, not just to things that might be space-like separated. They're causal connections that across things that might be what we call branch-like separated on different branches of history. But in any case, it turns out then that this, by understanding the dynamics of this kind of multi-way graph, it's very similar to the question of understanding the dynamics of the causal graph and being able to derive general relativity from that. And here's the thing, which for me is just an amazing fact, that if you look at essentially the turning of geodesics in this multi-way graph, what causes geodesics to turn in the multi-way graph is the presence of Lagrangian density. And just like what causes the turning of geodesics in the causal graph is the presence of energy momentum. Very similarly, the turning of geodesics in the multi-way graph is caused by the presence of Lagrangian density. And it turns out that, in a sense, what then happens, describe more detail later, is that the path integral for quantum mechanics turns out to basically be the Einstein equations, to be the same idea as the Einstein equations, but applied not in physical space, but in the space of branchings, what we call branchial space of this multi-way graph. So that's kind of a kind of significant thing. You can also talk about what happens with quantum mechanics and quantum computing and so on in the context of these multi-way graphs, and we can talk about how that works. And sort of the current state of things is, you might say, well, did you reproduce quantum mechanics? Well, here's the thing I can say. We just built a compiler that goes from our framework for quantum computing, which is the sort of standard quantum information framework, and simply compiles any circuit description into multi-way graphs. So in other words, that's sort of a way of showing the mathematical correspondence between quantum information and standard quantum mechanics and what we have in these systems. Okay, so what, there's a sort of a question of what happens, for example, how does cosmology work and so on. But let me, before we come to that, and I'll talk about that, so I wanted to just give you, actually, I'll show you one more thing here. So in this multi-way graph, each of these kind of nodes here represents a quantum state. And what we're seeing as we go down this picture is sort of the evolution of quantum states. When we take a slice through this thing, we're seeing essentially superpositions of quantum states. And what we have that is the analog of physical space is what we call branchial space, which is kind of a space of in which things are not connected by physical proximity, but they're connected by essentially entanglement proximity in quantum mechanics. So we can develop this kind of notion of branchial space, and that's a branchial graph, which is the analog of a spatial hypergraph. It's the analog of physical space, but in the space of quantum states. And it has this notion of an entanglement distances and so on that you can assign in this branchial graph. And so in a sense, the sort of the conclusion is that the Einstein equations are a description of what happens in the physical and spatial hypergraph. The path integral is a description of what happens in branchial space. And you can have all kinds of interesting things, like, for example, the speed of light governs the maximum rate of propagation of information in physical space. There's a similar speed, which is the maximum entanglement speed, which governs the maximum rate of information propagation in branchial space. And there are potential consequences of that, actually, I can try and talk about that might even, we don't know the scales of certain kinds of things, but we don't know this entanglement speed, maximum entanglement speed. I have a very kind of rickety estimate of it, which would suggest the maximum entanglement speed is on the order of 10 to the 5 solar masses per second. And so it is conceivable that, for example, one might be able to observe limits on black hole mergers that might be the result of not speed of light limits, but maximum entanglement speed limits, and so on. And there are various things like that that we can talk about. All right, let me go and perhaps go in a little bit more detail. This was sort of the big picture overview of how this works. I might say, by the way, that everything I'm talking about, we have this big website that has all of these documents, and all of the source code for doing all the computations and so on is all readily available, and I encourage people to look at it if you're interested. Okay, let's go in a little bit more detail. So let's talk about how these rules work, how we build up graphs and so on. Okay, so this might be a representation of something in the universe. We just have these elements here, and we have relations between elements. Here in this case, we have binary relations between a bunch of elements, collection of relations, binary relations between elements. And we can represent that by a graph here. And that's, and now what we think about is rules that say, whenever we have any element x and the same element x in another relation, and another element y, which might be the same as x as might not, and z, then we'll make this transformation. Okay, so that's all we do. So we can represent that by a something like this. It's just saying we are transforming that graph on the left to the graph on the right. So whenever we see a piece of graph that looks like the thing on the left, transform it to the thing on the right. Okay, so the question now is, what happens if we do that? So let's say we start from that graph there, and we just start applying that rule at every step. But it's a bit like my Rule 30 cellular automaton. Even though the rule is really simple, what you build up is not so simple. And so we run it for, I don't know, 10 steps or something, we'll get a thing like this. Now remember, what is this? So this is just a graph. It just says it has a bunch of points, and these points are joined, are connected in some way. The fact that the graph can be laid out in this particular way is just a consequence of how we chose to draw it. The only thing that is fundamentally defined is what the underlying pattern of connections is, okay? And what we need to now understand is, can that underlying pattern of connections, can this graph that emerges, how can that act like continuous space, for example? Just like we can say we've got this, bottle of water and it's got a bunch of molecules bouncing around. How can what emerges there seem like a continuum fluid? Okay, well, the details of what you get depend greatly on the rule you use. So for example, we can, I don't know, here are a few different rules. Here are kind of the versions of space that we get. Here are maybe a few others. The question is, when, how do we get something which, these things don't seem at all like space as we know it. So how do we get something that's like space as we know it? Here's one example. This is a particular rule. It operates in this way. There's a series of steps. If we keep it running for a while, it'll make this. So this particular rule is very convenient for us because it just knits this very simple two-dimensional pattern, or thing that is connected in such a way that we can reasonably say, oh, it looks like a two-dimensional pattern. Okay, so one question is, when we get some complicated mess like this, what can we even say? If we had a version of this as we think that might correspond to our universe, that's 10 to the 100 nodes of a graph like this, what could we say? Is it like three-dimensional space, or is it just some random graph? Well, a graph, remember, we can lay out a particular graph in many different ways, but we want to find some sort of invariant way to characterize how the graph works. So first question is, what is the effective dimension associated with a graph? So it's actually rather easy to work that out. What we do is we say, let's start at some point in the graph, and let's progressively go progressively further out in the graph, where we're just filling in, from every node, we go to the neighbors of that node, and we keep going, and we make this ball. We can think of it as a geodesic ball in this space. And so the question is, when we look at that geodesic ball, and we ask the question, how fast does that geodesic ball grow as we go graph distance r away, we go r graph steps, what is the growth rate of that geodesic ball? So if we do it in something which might be laid out as a three-dimensional graph, we'll find out it grows like r cubed. And in general, for a d-dimensional, for a graph that we can recognize that we lay out in d dimensions, that the growth rate of that geodesic ball will be like r to the d, that's the leading term. So we can compute for some weird graph like this. We can also work out what's the growth rate of that geodesic ball. And we can basically calculate the effective dimension of that space by asking the leading term of the growth rate of the geodesic ball is r to the d, fit d, you get the dimension. So for example, that thing that I showed you at first, it grows a spatial hypergraph that is about 2.7 dimensional. Okay, so that's how we can think about dimension in these graphs. What about things like curvature? So for example, we could say, by the way, if we have a graph that is a nice little fractal graph, we can use this way of measuring dimension, and we can find out, yes, it agrees with the Hausdorff dimension. This one's about 1.57 and so on. But it's just a way of measuring effective dimension for a large graph. Okay, so let's imagine that we have something, these are examples of graphs, and you look at these graphs and you say, well, those look like they're curved two-dimensional surfaces. Okay, how can we characterize that in terms of the structure of the graph? Well, the answer is that the subleading term, the next order term, the leading term, if we look at the volume of a geodesic ball, the leading term is r to the d. The subleading term, let me just pick up the actual subleading term here. Hold on one second. Should have this. Oops, that's not what I wanted to do. Hold on. Let me just pull in the actual, maybe. Oh, no, I don't. Okay, well, anyway, the next order term in that formula, it's r to the d, and then it's 1 minus r squared times capital R. Capital R is the Ricci scalar curvature, familiar from general relativity. So what that's saying is when you look at one of these graphs and you look at the growth rate of a geodesic ball, and this is, we're only talking about features of graphs here, but the growth rate of that geodesic ball has a leading term proportional to dimension, a subleading term that is associated with effective curvature of the graph. And so this is how we're going to start seeing how things like general relativity start to arise, because what's going to happen is that, well, okay, so the growth rate of a geodesic ball is proportional to the Ricci scalar curvature. The growth rate of a tube, if we make a geodesic between 2 points in this graph, a shortest path on the graph between these 2 points, and at every point on that geodesic, we construct a geodesic ball, the growth rate of that tube will turn out to be proportional to the Ricci tensor, essentially dotted into the geodesic that's the center of that tube. And so that gives us essentially this, I'm now assuming there's a bunch of relativity people here, but that gives us essentially the spatial Ricci tensor. Later on, when we talk about this in the context of the causal graph, we'll get the space-time Ricci tensor. And then what we're basically showing when we derive the Einstein equations is properties of the sort of how the large-scale behavior of the graph interacts with that feature of the graph captured by the space-time Ricci tensor. Okay, so by the way, we can talk about, I mentioned we can talk about geodesics on these graphs. They're just shortest paths between points on the graph. And we can talk about bundles of geodesics, and we can start asking questions about the fact that, you know, negative curvature causes divergence of bundles of geodesics and all those good things that we expect from standard differential geometry. Okay, so, well, maybe I should talk about, okay, let's talk about the causal graph. Let me see if I have a good picture here. Okay, let me simplify things a bit. And I have been talking about these hypergraphs, but let me instead talk about something much simpler. Let me just talk about strings, not in the sense of string theory, but in the sense of strings of characters, like strings of A's and B's and so on. And let me talk about how we might rewrite strings of A's and B's using some rules. So for example, we might use a rule that says BA is always to be rewritten as AB. So if we start off with some string of A's and B's here, then we can have a series of events, essentially rewriting events, where BA turns into AB. And if we apply a bunch of rewriting events, eventually they will succeed in sorting the string. So there'll be some pattern of events, and eventually they'll sort the string. Okay, but when we look at these events, one event here depends on the input to that event, depends on the output from this event here. So we can say there's a causal connection between this event here and this event down here. So we can represent that by drawing a causal graph, which shows that event there is causally connected to this event here and so on. So eventually this event down here will be causally connected to everything in its past light cone. And essentially what this causal graph is doing, it's defining light cones. It's defining for a given event, what other events can it have a future effect on? Okay, so what we're going to, so one question is, if we do these updating events in different orders, okay, in this case, we can do the individual updating events in a different order. And so but what will turn out to be the case is that whatever order we do it in, for this particular rule, it doesn't matter. The collection of causal relationships will be the same. So if you look at these different pictures, any particular update event will be in a different place. But the graph that you get out from all these different, updating events is always isomorphic. And so what that means is this property of causal invariance, that there's this property of causal invariance that says you can do these updating events in different orders, but you'll always get the same causal graph. This property of causal invariance, so let me explain a couple more things here. So let's go back to the multi-way system. So this is a very simple example of the multi-way system based on, again, this is based on string rewriting rather than graph rewriting. This is just saying the string A is going to be rewritten as BBB and so on. And then we just start off with the string A and it's rewritten as BBB, and then we apply the next, we apply it a bunch of steps, and there will be ambiguity in what we get out. So for example, the string BBB can be written in two ways, so it'll produce two results here, but those two ways turn out to converge at the next step. They both lead to the same outcome at the next step. So this thing that I'm constructing is what we call the multi-way graph. And there's a big question about the multi-way graph, which is what, for example, when there's a branch here, does it always merge or does it not merge? And that question of branching and merging is important. It turns out that there's this property of causal invariance is the property that any branch that happens will eventually merge. Okay. Now that property is something that is something actually that's sort of been seen before. So that's okay. That's showing the events that happen in the rewriting of strings. And what we can do then is to construct the causal graph that represents the causal relationships between those strings. And the big sort of property here is that when there is causal invariance, it will be the case that the causal graph that represents the relationship between those strings is always the same, whichever branch we effectively choose in here. So the main result is causal invariance implies same causal network, independent of what microscopic rewriting order we choose to apply. So independent of which particular rewriting rule we apply where, we will always get the same causal graph that represents that collection of relationships. Now, this is something slightly familiar. If it's familiar from mathematical logic, it's usually called confluence or the Church-Rosser property. It's also something it's a property that's been rediscovered at least a dozen times in different areas of mathematics particularly. But it's the property that, for example, if you're going to sort a string, it tells you that you can, and you're going to sort it by just transposing BA to AB. There are many different ways you can do that transposition, but it doesn't matter which particular order you do those transpositions in, you'll always eventually get the sorted string at the end. And we're kind of familiar with this kind of property from things like doing algebra. If you're expanding a polynomial, you can expand one part of the polynomial first or another part, but eventually when you get to the end, you'll have the same expanded polynomial out. So whenever underlying rules have this causal invariance property, this is what happens. And we get sort of the same causal graph. Okay, let's go back to our example here. Let's draw sort of a basic causal graph here. Okay, so imagine that this is our causal graph that represents essentially space across and time going down. And imagine now that we're an observer trying to figure out what's going on in this world where we as observers are also within the system. So we exist by our sort of process of observation also involves doing these events, just like the system we're observing involves doing those events. So in order to try and make sense of this system, we might try to decide, okay, what counts as time in our system? We might say, let's make a sort of foliation of this causal graph in which we say, this is what we consider counts as things that are happening at the same time. And we can consistently do that because, for example, these two events are time-like separated. They follow each other in time. This event always follows that event here. But these two events their ordering in time is not defined. Okay, so we can pick different possible, so we could say we're sort of an observer that's picking that foliation. We're maybe another observer that's going at that angle, and we can pick a different foliation of space-time. We can basically pick a different way of assigning coordinates, assigning space and time coordinates to these events. Well, what we have here is something that immediately looks very much like the standard derivation of special relativity, where we just straighten that thing out and we discover that we have, this corresponds to the observer sort of imagining a series of time steps, and you ask sort of how is this arranged in space. And so that in this sort of toy example immediately gives you kind of a Lorentz transformation. But what's sort of happening here is the fact that this picture has sort of the same physics as another picture is a consequence of causal invariance. Let me try and show you an example of that. Let's imagine that we have in our string rewriting system, let's imagine that this is our most basic kind of foliation, sort of the cosmological rest frame foliation. Let's now imagine that we pick a different foliation, let's say this foliation. Now we'll have a different sequence of events that we say happened. There'll be the same causal network of how these events are connected to each other, but these actual events will happen in different ways. Okay, but the fact that we get the same causal graph is a consequence of causal invariance. Okay, so what's happening here? So when we pick this different foliation, it's kind of cool because we actually see time dilation in the string rewriting system, and it has the standard factor that you can work out that what's happening here is just because of causal invariance, it follows that when you foliate in this different way to make a sort of different choice of inertial frames, you are forced to have exactly the standard kind of relativistic effect. So causal invariance is basically equivalent to the statement of Lorentz invariance if you assume that the observer is embedded in the causal graph. Now, in practice, for an actual system, things aren't as simple as that kind of toy version of the causal graph. There's a slightly more realistic causal graph, and the foliation of that slightly more realistic causal graph gets considerably more complicated, and there are all kinds of issues about how that works and about strong hyperbolicity and all kinds of other interesting properties of general relativity and so on. Okay, but in any case, the main point here is that by just looking at properties of this causal graph and this property of causal invariance, we're able to derive standard special relativity. I mentioned kind of the way that general relativity comes out. General relativity comes out by looking, and again, slightly more complicated story, but by looking at the growth rate of geodesic balls in what amounts to, it's actually the growth rate of cones. We're looking in this causal graph, we look at the light cones that start from a given point, and we ask the question, basically, what is the growth rate in the volumes of those light cones with time? And what essentially happens is that if we assume that the leading term in the growth rate of those light cones, if the leading term corresponds to a finite dimensional space, then it follows that essentially the subleading term has to vanish. And so that then establishes that, at least in the sort of vacuum approximation, that our R mu nu is equal to 0, corresponding to Einstein's equations. We can see that a little bit more physically by looking at bundles of geodesics, and by looking at sort of the statement of Einstein's equations is, in a sense, that the cross-sectional area of a bundle of geodesics always stays the same, although its shape may change. And that we can kind of see that fairly directly in these systems by thinking about that in those terms. Okay, so let's talk about, that's sort of a rough sketch of vacuum Einstein's equations. To get non-vacuum Einstein equations, we need an energy momentum tensor. I mentioned that energy is the flux of causal edges through space-like hypersurfaces. So these slices here are, at least in this frame, with this choice of frames, this is a particular choice of space-like hypersurfaces. We can pick any choice of frames that are consistent with the ordering defined by the causal graph. So essentially the causal graph is defining a partial ordering, and a foliation has to be consistent with that partial ordering. We can't have something where in a single space-like slice, two things that are time-like ordered are in the same space-like slice. But other than that, we can pick lots of different foliations, which correspond to lots of different reference frames. But in any case, what we're then doing is what we realize is that it turns out that energy seems to be identifiable with essentially the flux of causal edges that are these things here through space-like hypersurfaces. So in a sense, energy is a measure of the activity of the system as the density of activity in the system in space. But it's a little bit more complicated than that, because this causal graph is itself defining space. So in a sense, what this is saying is, what we're doing is the connectivity of this graph is defining space, and the density of connections in the graph is roughly related to energy. So similarly, if we look at the flux of causal edges through time-like hypersurfaces, that corresponds to momentum. And so one of the things we immediately derive is the fact that energy momentum transforms in the same way under Lorentz transformations as position and time, which is not something that's super obvious. It's something that you can derive from consistency with classical, with Newtonian physics and so on, but it's something that we can now derive from the underlying structure of this model. Now, one thing I should say is the way this model was constructed, time is a very different kind of thing than space. Space is kind of the extension of the spatial hypergraph. Time is this process of computation that applies the rules progressively in the evolution of the system. And it's completely not self-evident that from this thing where time operates very differently from space, that you will get something where you have things like Lorentz invariance or general covariance, where space and time are sort of packaged together. I think historically, the packaging of space and time together, which is mainly Minkowski's work from his work in pure mathematics and so on, was sort of a mistake, because it made people think you've got to think about space-time as a single thing, rather than thinking about time as this sort of inexorable computational process and space as just being the extent of something. Okay, but in any case, that's sort of a sketch of how that works, and you can in a crowd, please go ahead.
Could I say, I can't resist, I'm sorry, but like, could you explain how Heisenberg uncertainty comes into play here?
Not yet. I was about to talk about quantum mechanics, and I have a better.
Because I'm just trying to wrap my head around this, and it's
yeah. Okay. Right. So what I was talking about so far was classical physics. Okay, that's a great segue. Thank you for that question. Let me now talk about quantum mechanics. Okay, so as I mentioned, one of the features of I'll just mention one thing. What is an event horizon in these systems? An event horizon, this is a cosmological event horizon in the causal graph. Basically, what happens is there's a separation of two sides of the causal graph, and so this starts from the Big Bang up here, and then one part of the causal graph goes into this side, one part goes into this side, and there are no causal connections between them. And so we've started to classify the kinds of singularities that occur. It's really kind of cool. You can see like space-like singularities. I think I have might have some pictures here. Let's see if I have them up here. I'll pull it up later. You can start to classify various kinds of black hole singularities, and that things get a lot funkier in cosmology here because we're not dealing with fixed dimensional space. So in our models, the dimension of space-time is a dynamical quantity. It presumably for our universe is pretty accurately 3 right now. It probably didn't start as 3. In a bunch of our models, it starts infinite dimensional and gradually sort of cools down to ending up being 3-dimensional. And so that leads to all kinds of interesting, potentially observable cosmological features. And there's sort of a question of how you generalize things like general relativity and things like Riemann tensor and so on out of integer dimensional space. And that's an interesting math problem. All right, we've been asked about quantum mechanics. So let's talk about quantum mechanics. So the big point is quantum mechanics is all to do with this multi-way graph. So in classical physics, we say definite things happen. One thing happens, another thing happens as a result, another thing, another thing, another thing. What happens in these models is, it is an inevitable feature of these models, because there is ambiguity in which rewriting gets done. There are many possible rewritings that could be done at any given point that we build up this multi-way graph that says this is string rewriting, so it's simpler than the hypergraph case, that what we're saying is this was our Big Bang, then this thing got rewritten. There are two possible ways this could get rewritten, and then these get rewritten in these ways, and these ways, and these ways, and so on. And we see both branching and merging. So we see, and so now the question is, okay, so how do we think about quantum mechanics? The way we think about quantum mechanics is to think about each of these states as a possible quantum state. And so then the question is, what does it mean to have superposition? So what it means to have superposition is that we as observers, just like in space-time, we think of ourselves as having a certain reference frame in which we say this set of states exists at the same time. Well, it's exactly the same in quantum mechanics, and we call these quantum observation frames, or QOFs. And so this is something where these three states are viewed by us as being in a superposition. Now, there are many pieces to quantum mechanics, so let me poke at it from different places. This is an example of sort of how quantum measurement works in our models. Essentially, what one is doing is one is creating a quantum observation frame that essentially has a coordinate singularity. And that is what is causing sort of a classical, that one to have concluded that something definite and classical happened. One is then essentially freezing time there by the choice of one's quantum reference frame. As one freezes time, more and more stuff becomes incoherent. So there's essentially a decoherence effect that's happening at a certain speed that is in fact this maximum entanglement speed. So this is kind of part of the picture of how quantum measurement works. In actuality, it's considerably more complicated than that idealized picture. I just mentioned that when you're making a quantum computer, you want to preserve a pure state. And the way you preserve a pure state is to essentially make the analog of a black hole in this multi-way system. Okay, so how do we think about these multi-way systems? How do we think about all the various phenomena of quantum mechanics, like, for example, the uncertainty principle? So what we have to do is to think about how do we make kind of this is looking at, within a certain quantum observation frame, this is looking at the way we associate, the way we consider states to be related in that quantum observation frame. It's like saying, if we take a reference frame in space-time, how are points related in space, for example, in this reference frame? This is saying, how are quantum states related in the space of quantum states? How are they related in this multi-way graph? And so we call this sort of slice of the multi-way graph branchial space. It's the space of branches in quantum mechanics. And branchial space has distances in it, just like physical space has distances, except that these are now essentially entanglement distances. They tell us how entangled the two quantum states, rather than telling us how physically close are two states. And essentially what happens is, just like in physical space, we can ask, there's some light cone, and we can ask, how does one event somewhere affect these two different things that are spatially separated? We can ask the same thing in quantum mechanics. Okay, so we can set up the same kinds of ideas in quantum mechanics. So for example, if we want to know about, let's say wave-particle duality. Roughly what's going to happen is that a geodesic in this multi-way graph, which is something that is coming down, it's slicing through branchial space. So the geodesic, just like a geodesic in space-time, will be at a particular point in space, and it will change the point in space through time. So similarly, in this branchial space, the geodesic will move around in branchial space. So this geodesic will, just like in physical space, there's a geodesic, same thing happens in branchial space. Okay, so let's talk about the structure of branchial space compared to physical space. In physical space, we might try and do parallel transport. We might make a little rectangle with geodesics, and we might ask the question, we try and make a rectangle, we ask, does the rectangle close? And that will be a way of measuring the Riemann tensor in physical space, okay? So what will happen is, and that the Riemann tensor, the failure of essentially the commutator to close. The commutator in that case will be, we go in the x direction, we go in the y direction, then we go in the y direction, the x direction. We try and close that commutator. That commutator is equal to the Riemann tensor in physical space. Okay, so in the space of quantum states, we can also set up that kind of commutator. In our setup, these are quantum states. The events are quantum operators. And so we have something where we're just looking at, let's see if I have a good picture of that. We're just looking at, do I have one? Yeah, there we go. We're just looking at a state and two events here. This generates two intermediate states and it generates another event here. So this is something where we're saying these are quantum operators, and in this, so the commuting of quantum operators is a statement about what happens in this multi-way graph. And essentially what happens is the reason you get the uncertainty principle is for the same reason that there's curvature in physical space. There's similarly curvature in branchial space, and the uncertainty principle is the statement of the failure to have zero commutator, the failure to make that rectangle, but now in branchial space, to make that rectangle close. And the extent to which it doesn't close is measured by a curvature in branchial space, and that is what produces the uncertainty principle. So you can go and, so I mentioned before that if you start thinking about like an interference phenomenon or something, you can ask questions about how does something like that work? How do you get, and let me explain roughly how quantum amplitudes work. So a quantum amplitude is roughly, if you want to say, what's the amplitude to go from this initial state to this final state in quantum mechanics? So in our interpretation, what that corresponds to is you're at some state in this multi-way graph and you want to get to some other state. So you're going to follow some geodesic to get from one state to the other state, okay? And potentially you are going to, well, let's say there are, how to explain this? Let me tell you the conclusion and then I'll backtrack on how to explain it. The question is, how do you associate quantum amplitude with what's going on here? Well, essentially what you do is you say, you try and figure out path weights in this multi-way graph. So you ask, if you have one unit of sort of, 1 unit of input, and you just follow the multi-way graph at every step, just saying how many different ways are there to go to each point in the multi-way graph, you will build up in branchial space this measure, this weighting on branchial space, that is essentially the path weights that tell you what the path weight is to get to a particular point in branchial space. Essentially to get to that quantum state in branchial space, there is a certain path weight, okay? Now quantum amplitudes are usually written as complex numbers, and they have a magnitude and they have a phase. And it turns out that this path weight thing is the magnitude of the quantum amplitude. The phase of the quantum amplitude is associated with the position in branchial space. So it's actually a very different thing from the magnitude, but those two come packaged together in the standard formalism of quantum mechanics. So for example, when you have something like an interference phenomenon, what's happening in this picture is you have these two paths, and those paths end up being widely separated in phase. They are widely separated in branchial space. So the two geodesics end up being routed to essentially different ends of branchial space. And when you try and combine them to measure them, you end up getting zero, basically, because, and again, I'm now, there's a little bit of technical stuff here to do with completion. The idea of completions, which is an idea that comes from automated theorem proving, which is a way of taking what would otherwise not be a causal invariant system and making it causal invariant by adding certain additional relations. But by thinking in terms of those things, you can kind of understand why when you've routed these sort of geodesics to the opposite ends of branchial space, any measurement will conclude that essentially the weight of those things is zero. So essentially what's happening is that in the way to think about it, quantum processes, in this multi-way graph, you have this geodesics that represent sort of the evolution of quantum states. And these geodesics are being turned in branchial space. And that ends up with where they wind up, where their phase winds up in branchial space. Okay, so the turning of a geodesic in branchial space is essentially changing the phase of the quantum amplitude. So it's an interesting point that you might immediately notice that the path integral says that the rate of change, the change of phase is e to the I times the action. The action is the Lagrangian, is the integral of the Lagrangian density. So essentially what that's saying is the change of phase is associated with the local density, the local Lagrangian density is what determines the change of phase of the quantum amplitude. So in this picture, what's happening is the geodesic is coming through this multi-way graph, and it is turning in response to the presence of Lagrangian density. The reason it does that is Lagrangian density corresponds, is the sort of relativistically invariant version of energy and momentum. So think about it just like I was saying, that there's the energy is associated with the flux of causal edges through space-like hypersurfaces. The Lagrangian density is the divergence of causal edges in a region of the causal graph. And so what's happening is, whenever there is a density of causal edges, what it means is that there's essentially activity, there's connections being made in the causal graph. And those connections lead to those connections basically define where the geodesic will go. And so the more connections there are, the more Lagrangian density there is, the more the geodesic will be turned. And so that means that what ends up happening is, I'm just sort of giving you the qualitative version of this, what ends up happening is the rate of turning the geodesic is proportional to the density, to the Lagrangian density, and that's exactly what the path integral says. So essentially the picture is, in physical space, energy momentum turns geodesics. It's the same thing in branchial space. Because of the way it's set up with relativistic invariance, it's more Lagrangian density. If you did the Schrodinger equation, it would be energy again. But it's basically that's turning geodesics, and the turning of geodesics changes their phase because their phase is our interpretation of their position in branchial space. So that's roughly how that works. So for example, you can ask a lot of questions about you can ask about lots of kinds of things in quantum mechanics, but just mention one thing. Sort of a more cosmological kind, which has to do with black holes. And you can ask the question, okay, so what we've got here is we've got these two kinds of distance. We've got distance in physical space, and we've got distance in branchial space. So we can think about those as combined things. So this is kind of a picture of actually the multi-way causal graph, which is kind of the central object of this theory in the end, where it has time-like edges, it has space-like edges, and it has branch-like edges. So time-like edge is just one event follows another. A space-like edge is two events are consistently considered to be at the same time in space, and a branch-like edge, but separated in space. A branch-like edge is that they're separated by being on separate branches in the multi-way graph. So branchial separation, let's see how to explain this. Well, one of the things that's then interesting is when you have something like a black hole is a separation in the physical causal graph, in the causal graph that defines the structure of space-time. That separation, there can also be a separation in the branchial graph, in the multi-way causal graph. And essentially the relationship between those two. So what's happening in, for example, Hawking radiation, and we almost have actual pictures of this, not quite yet. We have a good qualitative version of this, but we don't yet have really nice examples. But what's happening is that essentially in branchial space, one is, well, it has to do with there's a physical event horizon in physical space. There is also an entanglement horizon that exists in branchial space. I mentioned that there's a maximum speed of a maximum speed at which maximum entanglement speed, and that defines, you can essentially have an event horizon with respect to entanglement, which is an event horizon in branchial space. In any case, the people are interested, we can talk some more about sort of how one resolves the sort of black hole information paradox by things being trapped between the physical event horizon and the entanglement horizon. We can also talk about how essentially at the entanglement horizon, an observer is sort of not able to form a classical thought about whether whether the particle went into the black hole or not. And that's a consequence of the way that this whole business about quantum observation frames works. Well, let's see, I can go on and talk about, there's lots of pieces to this whole thing. Let me make a couple of comments. So first comment is, one question is how far have we got in understanding all the different pieces of physics? We're slowly making progress on different kinds of things, like we slowly understood what angular momentum is in these models. We don't yet really understand the quantization of spin, although I'm pretty sure it's related to some homotopy properties in the multi-way causal graph, but we don't yet understand that really. That is deeply related to the whole fermion boson question, which I think is going to come out in a similar way. If you ask about the particulars of what we observe in our physics, okay, so one thing I didn't mention was particles. What is a particle in this model? So a particle is a localized structure that exists in the spatial hypergraph. And so it's easy to make sort of a toy model for particles. So for example, a good toy model would be to just say, imagine that you have a network where all the rewritings, which is a planar network, and all the rewritings that happen are preserved planarity. Whenever you have a lump of non-planarity in that network, it has a certain stability to it. And that's kind of the way that we think of particles, is it's sort of a, quotes, topologically, although we don't have ordinary topology here, a topologically stable structure in this spatial hypergraph. So we know from things like cellular automata, we know we have sort of good analogs here. So for example, in cellular automaton, it's a typical cellular automaton with an array of black and white cells. It's very common to get essentially these particle-like structures that emerge. Even though every cell is absolutely identical, you get these particle structures that are localized and, for example, move and interact with each other and have all kinds of elaborate conservation laws and so on. We expect similar kinds of things to happen in the spatial hypergraph. What we expect is that given a particular rule, we will have a particular collection of particles that exist in that rule, and it may be very non-trivial to find what those particles are. See, one of the problems with the whole business is this phenomenon of computational irreducibility. That is, you can't know how one of these computational systems will evolve except by explicitly following each step. That could bite us absolutely big time in trying to use these kinds of ideas to make a model of physics, because we could get to 10 to the minus 1,000 seconds after the beginning of the universe, and we could be able, and that could correspond to 1 billion steps of our evolution, but we don't know what's going to happen later because we have to actually run each step to find out. The thing that's been a big surprise to me in this project is that so much of what we've been able to figure out is generic to a large class of models. Once one has causal invariance, one has the essentially microscopic randomness, the essentially ergodicity properties that follow from computational irreducibility. Once one has causal invariance, computational irreducibility, the assumption that the universe will end up now being finite dimensional. With those three things, you can derive just a boatload of stuff. And those three things alone give you relativity, quantum mechanics, etc., without any additional knowledge of the underlying rule. Now, probably things like the detailed masses of particles will depend on the underlying rule. I suspect things like spin statistics connection will not. We know something about how CPT invariance works in these models. It again doesn't depend on the specifics of the underlying rule, but there'll come a point where we kind of have to address what is the actual underlying rule, and that can get complicated. Now, there are a few generic things you can say. So for example, one thing I think might be of some astrophysics interest is the question of, well, what might the collection of particles that exists in this model really be like? So we don't know in detail, or I should say another thing. One question you might ask is, well, what is, for example, in the spatial hypergraph, what is the elementary length? What is the elementary time? We don't know for sure. We know it's a lot smaller than the Planck time, because it turns out the Planck time, so one of the sort of mysteries about Planck units and so on is that the Planck time is nice and short, 10 to the minus 34 seconds. 43 seconds. But the Planck energy is quite big. It's about the energy of a lightning bolt, and that's always seemed rather mysterious. in these models, the scaling of things works a bit differently because essentially the Planck energy is associated with all the parallel threads of quantum mechanics operating together. And so we can sort of unravel that, and we can make some estimates based on the size of the universe and various other kinds of things. We can make some estimates of these things, and we finally get estimates of what the so the elementary time, I think, I have to look this up, I should know this. I think the elementary time ends up being 10 to the minus 101 seconds. And the elementary time is so 10 to the minus 100 seconds is the elementary time, roughly, maybe, in this sort of set of approximations. And so one of the things that, and then, for example, the electron has a non-zero radius. Its radius is 10 to the minus 81 meters. So one of the non-trivial facts about that is, if that's right, it means that the electron has your average electron has a large number of edges, a large number of causal edges within that electron. And so that means that one might think that there will be particles that are, in a sense, much smaller than the electron, a whole zoo of particles of much lower masses than the electron. And that's not something that usually comes up. I mean, there are mechanisms that give you light neutrinos and things like this, but the idea that there's a whole vast zoo of lighter particles is not something that's really been naturally thought about in particle physics and so on. But one of the implications of this model is there's probably a vast zoo of much lighter particles. And so we call them oligons because they involve a small number of edges in the spatial hypergraph. And so there's a question of what the astrophysics and cosmology of oligons is, and you can kind of work out they decouple very early in the history of the universe. They end up being quite cold. They potentially are decent candidates for dark matter and so on. But there's a lot of astrophysics to actually do to work out their detailed properties. In these models with respect to cosmology, there's a lot to be said about sort of this cooling down from the likely infinite dimensional state of the universe at the Big Bang to something three-dimensional, and the implication and the questions of when the decoupling of things like oligons happens with respect to that sequence is an interesting one. There's also questions about whether at the sort of last scattering surface or whatever, whether there actually is still any signs of sort of density perturbations that might be left over from the underlying structure of sort of the first few rewrites that happened right at the beginning of the universe. Those are fun questions. My guess is that the answer to that is no, that essentially there will be so much computational irreducibility, which, by the way, is what leads to thermodynamic equilibrium. In these models, there's a direct connection between computational irreducibility and the second law of thermodynamics. The second law of thermodynamics is essentially a consequence of sort of the encryption of initial conditions through computational irreducibility. That's why the entropy appears to increase, because you're not able to sort of, you as an observer don't look at things finely enough and with enough computational effort to be able to decode what's going on there. So I just mentioned one more thing, and then I should wrap up, and I've probably been going on way too long, and I haven't been looking at a clock, and that's always bad. I have here, I think I had a table. That's really weird. Okay, that's a piece of reveals the innards there, but that's, okay, 10 to the minus 101 seconds for the elementary time, and so on. The spatial hypergraph, pretty big, 10 to the 350 nodes, and so on. Okay. I mentioned one more thing that's kind of funky and then stop, which is the question of, let's say we succeed in finding a particular rule for the universe. Then the obvious next question is, why do we get that rule? We get rule number 10,314. Why do we get assigned that rule? Why did our universe get that rule? And particularly if the rule is simple, boy, that's really kind of weird because, there's an infinite number of possible rules. Why did we get a simple one? I mean, back from the time of Copernicus, we've sort of learnt there's not really anything special, it seems, about our place in the universe, so to speak. And so wouldn't it be weird if our physical universe, in the computational universe of all possible universes, if we got assigned a simple universe out of the computational universe of all possible universes? That would seem very weird. So I thought we'd not be able to resolve this question. But actually, it turns out I think we do have a resolution to this question. So I think what happens is that I've talked about how we have a particular rule, but it's applied in many different ways, and that's what leads to quantum mechanics and so on. Well, imagine that as well as applying a particular rule in all possible ways, imagine that we applied all possible rules. Then we would get this really complicated mess here with all possible rules being applied. But now, it turns out when you apply all possible rules, you almost inevitably have causal invariance. And that means that essentially you have a sort of rule space relativity, and it doesn't at some level matter what choice of reference frame you make in describing your universe. And so we have this notion of what we call ruleal space, which is just like branchial space is the space of all possible branches within a single rule. Ruleal space is the space of all possible branches with respect to sort of all possible rules. And I just, let's see if I can pull this up here. Where did that go? Wrong place. Okay, so the study of this kind of ruleal space of all possible rules. So how do we, what then is our view of the, so what happens in physical space, different choices of reference frames correspond to the standard things with motion or assignment of gravitational fields and so on. In branchial space, they're associated with quantum measurements. What are they associated with in ruleal space? What are the different choices of reference frames associated with? They're basically associated with different description languages for talking about the universe. They're associated with different ways, different sort of ways you can describe what you observe in the universe. And so when you are sort of moving from one ruleal reference frame to another, it's like changing your description language. Well, we, as a result of the physics we've done and so on, and the result of the senses that we have as biological organisms and so on, we have picked, in a sense, a particular frame in ruleal space, a particular description language, which corresponds to sort of our view of the universe. So for example, one feature of our view of the universe is at the size we're at and our brains and the speed of light and so on, it's reasonable for us to talk about things happening simultaneously. That is, the speed of light coming to our eyes, of the things we see when we look around, if you're not astronomers at least, the things we see effectively seem to come to us. Everything in space seems to come to us instantaneously because the speed of light is very fast compared to our brain processing speed. If we were a different size, different sort of form factor in the universe, we might conclude differently. We might have a different set of descriptions of what's going on. And that's the kind of thing, but you can take a much more extreme version of that. You can ask for sort of the extreme version of how you get a different way of describing the universe. And those correspond to the different choices of ruleal frames. And in a sense, the reason then that sort of we have our description of the, we hopefully get a particular rule to describe the universe is that's the rule that corresponds to our particular frame in ruleal space. And it's there's sort of an overarching system which provides all these possible rules, but we get the one that corresponds to the frame we've chosen. And that, let me show you something that I just recently did. So I've been sort of exploring ruleal space, and actually you can explore it in terms of Turing machines. So you can explore the space of all possible Turing machines, just as an example of a space of all possible rules. And this is, let me show you an example here. This is from something I just posted yesterday, I think, day before yesterday, maybe. This is ruleal space. This is a multi-way causal graph in ruleal space and the space of Turing machines. Here's an interesting thing, perhaps. Well, this is showing the difference between ruleal space, which is essentially the extreme non-deterministic Turing machine, and the possible paths. So a Turing machine, an actual deterministic Turing machine follows a non-geodesic path in ruleal space. But it's sort of an interesting thing that you can, this is a geometrization of the P versus NP problem, basically. The limit of this shows sort of the difference between what you can reach with deterministic computation and non-deterministic. But the main point here is it's just the beginnings of trying to understand the structure of this ruleal space, the space of all possible rules. But our particular view of the universe is based on this particular slice that we make through this space. And even though in the end, the only thing that is sort of a constant fact that is true for all slices that we might make through this ruleal space, the only sort of final result that is essentially, well, is this thing I call the principle of computational equivalence. which is one of whose consequences is the existence of universal computation. In a sense, the one sort of constant fact is that the universe is computational. The particular rule that we attribute the universe to having is a consequence of this particular description frame that we use. But anyway, all right, that was a much longer than I expected sketch. You see, I haven't done this very often. I used to give physics seminars all the time, but that was 40 years ago, and I'm deeply out of practice at doing this. So it's and also I have the full story here is long and getting longer by the day, so to speak. But that's sort of a sketch of what we figured out so far. I'm sure I forgot a few big things, but that's kind of the picture, from this sort of simple rule to this notion of kind of a discrete spatial hypergraph, to this idea of this multi-way graph that corresponds to that gives us spaces of quantum states, to the various consequences of that, and sort of thinking about the continuum limits of all these things. And I should have said that you know, for example, it's quite likely that the continuum limit of the multi-way causal graph is related to twistor space. It's likely that a bunch of, well, for example, the ADS-CFT correspondence seems to be deeply related to the correspondence between physical space and branch yield space in the multi-way causal graph. There are a bunch of these things that are sort of known features of modern mathematical physics that seem to have direct analogs in this theory. And in a sense, I view this theory as being kind of the low-level machine code that operates sort of below the level of description that is being explored in a lot of kinds of things that have been done in mathematical physics. All right, I should stop there. I see there was a big accumulation of comments or questions on the chat, which I have not been looking at. So please, I'm happy to try and answer questions.
Thank you so much, Stephen. This has been a great excursion into the branchial space. So I'm sure we have many questions. So before we go into the Q&A, I would like to give the floor first to our panel members here.
Yes, I wasn't sure what this panel was doing, but please, I'd like to hear from them.
Very alive in the background, yes.
Okay, good.
So maybe I can ask, like, to start with the first question. So of course, I mean, it's a beautiful architecture that you're developing here. Is there? I'm intrigued about this 10 to the 5 solar masses per second branchial speed. Can you give us an intuition for the predictive power of this construct? Like, so how could we tie this to experiments, to observations, to verification,
right.
falsification? Right? We have 5 8-meter telescopes in the background here. Let's make use of it.
Right. That would be very cool. I would love that. I mean, so here's the thing. So, you know, in the evolution of science, what tends to happen when big new theories get developed is, first step is theoretical predictions. Sure. That is, can you reproduce what's already known? You know, before you start getting predictions. Now, I think that what's happening here is we kind of and the first step in theoretical predictions is, do you run into places where you have to make kludges? So, you know, do you find out, oh, this theory, it's all very nice, but, you know, it requires that we explain why we don't have 10-dimensional space or something. And then you've got to have some whole kludge tower. So far, no kludge towers, which is just amazing. I mean, and that's why I'm increasingly confident that we've really got it. Because, you know, what we've run into is a lot of things where it's difficult. You know, we're trying to understand, how does local gauge invariance work, or we have to understand how Lie groups arise from limits, from buckets of permutations and things. It's complicated, but there's no, oh, you can't get there. Okay. Now, in order to make predictions, so the question is, are there scaleless predictions that can be made, or do we need to know the scales of everything? Right. So Einstein was pretty lucky in general relativity because he had a scaleless prediction. He had the prediction of the bending of light around the sun, where it was, you know, gravitational magnetism makes a factor of 2 difference in the amount of bending, right? And that happens to be scaleless, right? But there are other predictions, like, you know, if he'd had to predict, if he'd needed the value of the cosmological constant, he wouldn't have been able to make predictions because he didn't know the scale of the cosmological constant. So the question is, what scaleless predictions can we make? And then what predictions can we make if we assume a scale, or even if we say, let's do something, we don't know the scale, we don't know if we're going to find something, but here's at least a thing to look for. Okay, so in terms of scaleless predictions, we haven't really worked on this as much as we might. But I have a suspicion that there are some scaleless predictions to do with things like photon correlations in orbits around, photons in orbit around a black hole, that there will be correlations that will be different as a result of the existence of this entanglement horizon than they would be in the case of a pure classical horizon. And that might be a scaleless prediction. That might not matter what the actual scale of the maximum entanglement speed is. So that's one type of thing. Another thing is these kind of funny predictions, like this oligons idea. It's not a strict prediction of the theory, but it suggests looking for particles that are vastly lighter than the electron, a big spectrum of such particles, and looking at the astrophysics of those, and possibly looking at the phenomenology of what such particles would you know, because we can say things about their interactions and so on, even without knowing a lot more. There are other predictions in quantum computing, actually. Again, it depends a bit on the scale. We can make theoretical statements about quantum computing. So I worked on quantum computing first back in 1981, before anybody had really heard of quantum computing. And I was very skeptical. I always thought that the measurement process was going to remove any gains that might have been made through the sort of process of parallelism in quantum mechanics. And we now have an actual theory where we get to describe how measurement works. Usually in quantum mechanics, it's like you do all the quantum mechanics and then, you know, bam, you do a measurement, and that isn't really described as part of the theory. But we now have a theory where there are actual, you know, every step of the measurement is as described as the process of the actual quantum process. And the speculation of the week, which may not turn out to be correct, is that you actually don't ever gain anything in genuine quantum computing. Doesn't mean it isn't worthwhile to look at the physical effects of quantum mechanics for computers. That's an important thing to do. But from a theoretical point of view, the quantum mechanics is sort of a branching out in multi-way space, in branch Hill space, but then the measurement is trying to corral back all these things, all these little pieces that have branched out. You've got to corral them back into something that you can consider as a definite classical measurement. And the current speculation is that you will never gain anything with that, except by virtue of the expansion of branch Hill space. So just as the universe is expanding in physical space, it's likely the universe is expanding in branch Hill space. Branch Hill space is probably exponential dimensional and probably has in some sense a much faster expansion rate. We don't know its cosmological constant. We don't know, you know, we know very little about it. But imagine that you wanted to, imagine you were doing an energy game in the physical universe. You might say, well, energy isn't conserved. After all, the universe is expanding, and we could, for example, we can attach a spring between two black holes at the center of two distant galaxies, and as the universe expands, it's going to put potential energy into that spring. And gosh, that's a way of getting energy out of the vacuum or something, or out of the using up the energy of the Big Bang for our own purposes, so to speak. Well, I think that quantum computing will end up amounting to the same thing, that insofar as you get an advantage, it's because of the expansion of branch Hill space. And that it may in fact be numerically significant, I don't know, but that's the kind of qualitative way to think about it. Now, so there may be predictions about the rate of decoherence in quantum computing. We don't know if there'll be, what the scale of that is. Now, this overall scale, this elementary time scale, the current calculation that we have is, I think, is kind of rickety. It might be correct, but I wouldn't stake that much on it because it's based on a bunch of assumptions and so on, although very conveniently in the middle of it is a transcendental equation which has a bizarre lack of dependence on actual parameters. So it's an equation where the answer is right within 10 orders of magnitude or something, but without, it's very insensitive to a bunch of parameters. But it's just a fortunate thing that happens, that arises there. Okay, so once you have the scale, you can do all kinds of things. Once you have the scale, you can make all kinds of, well, in particular, again, lots of actual work to be done about, for example, black hole mergers. Okay, so the issue is black holes are merging, the speed of light determines how fast certain things can happen, but the maximum entanglement speed also determines that. And I think there may be a difference in what happens there. Let me mention another thing, which is in the nature of theoretical predictions. So in numerical relativity, there's always these issues about how do you do numerical relativity? How do you set up the right meshes and grids and all this kind of thing? So, okay, we have a suspicion that our causal graph is a really good way to do numerical relativity, because it already contains, unlike rigid calculus and things like that, which were traditional discretizations of the Einstein equations, the causal graph essentially has gotten rid of the gauge degrees of freedom that sort of plague a lot of kinds of approaches to numerical relativity. So one of the sub-projects that actually Jonathan Gorod has is to try to make a practical, general relativity code that's based on our causal graph, which means we're taking, it's just like back in fluid mechanics, I invented a method back in the mid-1980s for doing fluid mechanics, where instead of taking the Navier-Stokes equations and discretizing them, you start from a molecular dynamics based on a very simple cellular automaton, and then you just scale that up. You just say, take the averages across large numbers of these sort of computational elements. And so the idea here is actually use our theory to make the numerical scheme, to make a consistent numerical scheme, kind of working up from the atoms of space rather than working down by discretizing the Einstein equations. So that'll be an interesting, again, in terms of sort of theoretical predictions, I think it's okay, so if you want to know, does our theory really reproduce general relativity? Obviously, you can read the mathematical derivation, but it's much cooler if you can actually say the code that's being used to compute some black hole merger is based on this causal graph, and it's just, comes from this model. And that's a sense. Now, it doesn't really give you anything different from general relativity because we already knew this model reproduced it, but it gives us something interesting. And one of the possibilities there is that we might be able to do the same thing in branchial space for the path integral. And that's a much less trivial thing because lattice gauge theory is always done in Euclidean time. It's always done in this sort of fake imaginary time situation in which space and time have the same signature. But if we can essentially use our multi-way causal graph as a discretization of quantum field theory, we can potentially do sort of numerical quantum field theory directly in Minkowski space, which again will be pretty interesting. But the answer, let me just say that I fully expect at the summer school that we have coming up in a couple of weeks, I know we have some astrophysics folks coming to that. I fully expect that we will actually try and dig into actually working out, even if we don't know the scale, even if the scale is arbitrary, what effects can we see? Like, for example, density perturbations in the early universe. That's a potential thing. As I say, I think they'll be washed out, but we're not sure. This question of infinite dimensional early universe going down to lower dimensional, there may be some signature of that. I think the most, another possibility is a signature of dimension fluctuations in the universe. So we don't usually think about dimension fluctuations. We're stuck in 3 dimensions and we think about curvature. Curvature and dimension actually trade off against each other, as you can see in these formulas for volumes of geodesic balls and things. And so it is in fact possible that there's even a whole description of general relativity that is not in terms of curvature, but in terms of dimension change. I don't know yet. That's a question that requires a bunch of mathematics to be developed. I mean, calculus is really the study of things, manifolds and so on, are all about things which are locally like interdimensional Euclidean space. We don't have a theory of things which are locally like fractional dimensional space. So we don't know the analog of the Riemann tensor, for example, in fractional dimensional space. I mean, we do from this theory. We actually have, we have a derivation of what it is in this theory, but we don't have from sort of traditional mathematical differential geometry, we don't have that. But so one possibility is that you could reformulate general relativity in terms of dimension change, a local dimension change instead of local curvature. That's one possible interesting thing. Another possibility is the possibility of dimension fluctuations in the universe, and dimension waves in the universe, for example, is another possible weird thing. There are also all kinds of singularities that can exist in space-time that are extremely exotic from the point of view of general relativity. So for example, one kind of singularity is a dimension change singularity. So one of my favorites is this thing I'm calling space tunnels, which is something where you have essentially a tube in space-time that is a higher dimensional lump of space. And so you get all kinds of weird wormhole-like things, but they're very different from general relativity. They're not classified by the standard singularity theorems of general relativity and so on. There's something different. And we don't know what they are. I just started trying to work on classifying some of these things. It's not easy work, and it's not helped by the fact that the mathematics really doesn't exist yet. So those are so looking for some of those kinds of, for example, dimension anomalies would be really interesting. We don't know what the consequences of those would be. I would say, let me make one comment about dark energy, dark matter, and the structure of the universe at that level. So, one of the mysteries about the merger of quantum field theory and general relativity has been, why do the vacuum fluctuations implied by quantum field theory not roll the universe up into a tiny ball? I mean, this has been one of the sort of fundamental questions, because, quantum field theory says there's an uncertainty in the number of particles that exist. That's sort of an inevitable feature, that there's this 0-point fluctuation in the number of particles that exist, and that means that there's a huge vacuum energy, which we get rid of in quantum field theory by doing normal ordering and so on, by just sort of saying, well, it's everywhere, so we don't have to worry about it. But if we try and be honest about sort of the gravitational effects of quantum field theory, we would expect that, we'd get this huge energy density, I don't know what it is, 10 to the 120, I forget. We can predict what it should be based on known particle physics. But we don't see that, because our universe isn't rolled up in a tiny ball. So how does that work in our theory? So the way it works in our theory is kind of interesting. The way it works is that in our theory, all those quantum fluctuations that are happening, they are what make space. So it isn't the case that we have in space, we have matter that's having all this effect on space. What we're saying is that the actual processes that are going on that correspond to those quantum fluctuations actually are the things that make space. So that means that that's why you don't have a situation where you have the space and then you have all of this energy momentum that's causing the space to curl up. Because when you work out, when I talked about deriving the Einstein equations with energy momentum, what that actually is a difference of energy momentum between the energy momentum that we can attribute to the maintenance of space and the energy momentum that we can attribute to matter. Always in the Einstein equations, there's sort of a trade-off there. You can say, I'm going to move the gravitational wave piece of energy momentum from the T mu nu into the R mu nu and so on. And that's a sort of typical general relativity kind of issue, and we have the same thing. But anyway, the end result is that in our universe, and again, with the scaling that we have, it's kind of a disappointing thing. If we look at all the activity in our universe, and we look at what fraction of it is just the maintenance of space, and what fraction of it is actual matter and particles and things, 10 to the minus 121, 1 part in 10 to the 121 is actually anything we care about in the universe. And all the rest is just the maintenance of space with the scaling that we have here. But
So if you take lambda, right, if you take the expansion of space time, does that mean that the nodes or the node density in the branchial space is increasing constantly? Do we have ever, let's say, a chance to dig into the fundamental level?
Okay,
right?
so well, so I mean, the likelihood is that the spatial hypergraph is expanding, that the number of nodes is increasing at a rapid rate. Okay, now I have to say I am trying to avoid an Einstein mistake. Okay, because the most natural way that this model works, it leads to rapid expansion of space. Okay, so as you might remember from the history of general relativity, that's what Einstein concluded from his original equations. And he said, but that doesn't happen, so let me add a cosmological term, right? So similarly, we have this issue. The most natural way to set up these models, the number of nodes in the spatial hypergraph increases rapidly with time, okay? But, I have all these mechanisms for thinking about other rules that reduce the number of nodes, et cetera, et cetera, et cetera. But if it isn't the case, if it's the case that the number of nodes increases rapidly with time, here's the following incredibly bizarre thing that potentially happens, okay? So there's this whole dichotomy, is space continuous or discrete? Okay, well, if the number of nodes is increasing rapidly, what can happen is that any 1 meter, I've said there's a certain elementary length, but maybe maybe the number of nodes that correspond to a meter is actually increasing. And it's, in other words, that the things we measure, the sort of topological excitations that correspond to particles, things like that, not affected by this because we're just measuring the sort of topological features. But if we just want to count the number of nodes, it might actually be increasing rapidly. In what we consider as 1 meter, it might be increasing rapidly. So we'd have a very bizarre situation where basically the fineness of space is rapidly increasing. Not only is space expanding as a whole, but also the fineness of space might be increasing. And it's kind of a weird thing, because it could even be the case that if you set up a measurement to try and see the discreteness of space, it could be the case that by the time your measurement can happen, space will have subdivided to the point where it will be less discrete than what you were measuring. So it's kind of the ultimate physicalization of the sort of calculus epsilon delta argument, where your space is taking that limit. But so the answer is we don't really know. We don't know. We certainly can't estimate something like lambda. We can get an idea. I mean, it's sort of interesting to try to understand. Okay, so I have another bizarre idea which I don't think is realized in these models, which is the idea of what we might call vacuum cleaners. So in other words, if you have if you have an actual structure that represents space, then there's the question of, could you have a vacuum cleaner that will reduce the density of energy in space? So in other words, because you have a space that actually has effectively energy density in it, you could imagine, having a region of space that has a smaller, density, and that will lead you to, that's essentially a dark energy type situation where you've got a reduction in the density of energy in space, but we don't know how that works. And again, I have to say, I'm just waiting for the point where we run into sort of computational irreducibility and where the next steps are really hard, because we have to actually find specific rules and do computations and so on them. But so far, we're still sort of in this situation where we're able to make generic statements that sort of sit on top of the computational irreducible substructure. We're able to make generic statements that sort of map into current mathematical physics. And I wouldn't be surprised if we could make a few more statements about sort of dark energy, dark cosmological constant, these kinds of things generically without having to know the specific rule. But it's just a lot of, it's worth remembering that in the origination of general relativity, it took a little while, to put it mildly, before the full implications of general relativity were understood. I mean, it basically took until the 1960s for lots of things to be decently understood. And I'd like to think that we've got better tools and better mathematical physics and so on, but it's still, this is a very low level theory. And so to build up to things that you can actually measure is non-trivial. But I really am keen to kind of brainstorm with people about sort of cosmological, astrophysical types of things that might be relevant effects. And I think these kind of anomalous structures in space-time are one thing. They may exist, they may not exist, but this at least gives you a reason to look for them. And some of these effects in exotic situations, like in black hole mergers and so on, is another one.
Okay, so let's give Carl the word here.
Hello, Stephen. I'll try and be brief because we've been going for a while now. I gather the translator is getting a bit tired as well.
Sorry, and I talk quickly, and I apologize for that.
Patricio is our trooper here.
My question is about Bell's inequality. So Bell's theorem says that properties of quantum entanglement are not compatible with a local hidden variables model of quantum mechanics. So I guess your theory is non-local in some sense. So perhaps you could explain a bit about what that sense is.
Well, okay, so the point is that this multi-way causal graph is something just very different from what's been considered in standard kind of setups of Bell's inequality. Actually, we're in the process of writing up some nice clean derivations of the violation of Bell's inequality and its generalizations and so on. It actually works out rather nicely in these models. What's the best way to kind of start describing this? I think, okay, I don't have the cleanest way to describe this yet. The basic point is that, what we have is a deterministic multi-way graph, but the particular structure of Bell's inequality is just based on a theory that's really of a different structure than this. Let me try and give you at least my current intuition about this, okay? So I think the way to think about Bell's inequality is to say, if you observe, let's think, if you observe a certain, so in a string rewriting system, you might say you observe a certain sequence of strings that get produced. And the question is, does there exist a deterministic model that just gives that sequence of strings? And in the multi-way graph, what we're asking is, there are many possible paths that can be, I'm not doing very well here. this is the answer is we will soon have something written which is a nice formal derivation. I think one of Jonathan Gorod's papers about this actually has a fairly formal description of how the CHSH inequality, which is sort of a generalization of the Bell's inequality thing, works. It's not very profound. I mean, in other words, it's really just a consequence of the fact that this model is just of a very different character than what was imagined in the setup of Bell's inequality. And I don't think that the, you know, it's deterministic, but it's in some sort of super sense of determinism, in the sense that the set of all possible states is deterministic. But that's like saying the Schrodinger equation is deterministic. That's not addressing the interpretation of the wave function in the Schrodinger equation. It's not a great answer. I will have hopefully in a month I will have a cleaner, better answer. There's the beginnings of a nice argument in terms of string rewrite systems to understand sort of intuitively what Bell's inequality is and why it gets violated by these systems. But I'm not going to do a good job here. Sorry.
Okay, so let's continue with Sergio.
Yes.
Actually, I'm sorry. I was going to say that on the Q&As for this on our website, there is a probably better description that was probably written by Jonathan about the Bell's inequality question, and I recommend looking at that. And I'm sorry I couldn't do such a good job there. Okay, please go ahead.
I was wondering about the parameters. So between the number of parameters you need to scale up the model and the number of parameters you need to select what rule, how many you estimate there are compared to something like the standard model or something like that?
Okay, so there are two things. One is these sort of aggregate parameters that map our models onto the physical world, and the other is the underlying rule, okay? So when it comes to the underlying rule, there's an infinite number of possible rules. And we have no fundamental reason to think the rule is simple, right? And if, it could be arbitrarily complicated. It is merely a guess that the rule is simple. So with respect to the rule, I mean, there are trillions of possible rules, but each rule, one feature of these rules is the things that they lead to. We have kind of a fun thing on our website that is called a registry of notable universe models, okay? And these are all different particular rules, and they lead to bizarrely different behavior. So the distance between one simple rule and the next nearest simple rule is very large. So that's kind of you don't really get parameters in the usual sense. You don't get to adjust, to tweak knobs. It's like you've got this rule or you've got the next rule, and they'll have just completely different properties. So that's first thing to say about the underlying rule. The second thing is about the connection to actual measurements we make. There are basically, well, there are two important parameters that determine the relationship of these models to everything else. Well, there's only one that we don't know. Okay, we know the speed of light, we know Planck's constant, we know the gravitational constant, we know how Planck units work. The one thing we need to know is the maximum entanglement speed. If we knew that, we call it zeta. If we knew that value, we would have all of the parameters. Now, the details of things like particle masses and so on, they presumably come out of the underlying rule, but many features of, for example, what's our maximum entanglement speed, how does that relate to black hole information and so on, that is all just a result of one parameter, just one. Now, there's an additional parameter, which we call rho, which is the maximum speed in rulal space, which is a much more bizarre thing. That is the thing that knits together. That parameter essentially gives us the computational processing speed of the universe. And that parameter, I don't really know its physical significance at this point. I think its significance has to do with, it's a very bizarre thing. I mean, it has to do with, if you are changing your description language, what is the maximum rate at which you can change the description language you're using? So that's a thing far away from current physical experiments. The maximum entanglement speed is absolutely much closer. It may turn out to have a value that is not readily accessible experimentally, but it's just one parameter. So that's the setup. Now, okay, so the other thing, once we have the rule, there's also a question about initial conditions. I think, you can trade off rules and initial conditions. You can put the information in one place or the other. But the rule, you have to sample this whole space. and we don't know where it is there. But it's not a tweakable thing. It's like it's either going to be, you know, the distance between neighboring rules is bizarrely large. Like one of them will have exponential dimensional space, one of them will have two-dimensional space, one of them will have, you know, no communication between different parts of the universe, one of them will have just very, very great differences. So it's not something where you get to tune, you know, the value of alpha sub s or something like this in the standard model. I mean, by the way, go ahead. I mean, you know, once we start having, I would say the particle masses, once we start getting particle masses, then there are a large number of arbitrary parameters in the standard model. Basically, the mass of every supposedly now elementary particle is an arbitrary parameter in the standard model. It's just, you know, it is parameterized as the Higgs coupling of that particle in the standard model, and it's completely arbitrary. So, you know, in our models, they will not be arbitrary. We you know, the choice of rule, we don't know it, but once we have a rule, those particle masses will be completely determined, all of them. And, you know, how difficult it will be to compute them, given the rule, we don't know that, but we don't get any wiggle room there.
So let's continue with one question here with Chris from the panel.
Yes, thank you very much, Stephen, for a very nice talk. Yeah, my question is very similar to the previous one, and it's a little bit more general. So it seems like a lot of what you talked about is predictive behavior in terms of explaining physical law. And I'm just wondering about how it might connect to the standard model of particle physics. You said a little bit about it, but in a more general sense, is it able to explain anything about that? You mentioned the masses of things, but about the other aspects of it, about different families and bosons and fermions and those kind of things.
Okay, so let me break those apart. And okay, specific particle masses, we don't know anything yet. Fermions and bosons, we don't yet know, but we think we're close on that one. The one that I think is probably more accessible is local gauge invariance and the local gauge group. So we pretty much know how local gauge invariance works, and it's interesting. I mean, it's basically just as when you're making, when you do these rewrite rules, there is basically a local freedom in how the rewrites happen. And that local freedom is what we believe corresponds to local gauge invariance. And you can kind of see qualitatively, if you sort of do one rewrite in a particular place in the spatial hypergraph and it goes one way, that kind of constrains the way that rewrites go in other places, although each individual rewrite is arbitrary. And that's kind of the way that local gauge invariance starts to work, and the way you start getting connections in the fiber bundle and so on. You can build up the whole sort of standard mathematics of fiber bundles and local gauge groups and so on the basis of these models. It's a little bit mathematically Wild West, because standard fiber bundles and things live on interdimensional spaces. Nobody knows what they do in these other cases. So we have to invent the mathematics along with the physics. But this is fairly typical for physicists, I'm afraid. The mathematics gets invented as part of the physics, so to speak. But that ends up being, I think so local gauge invariance, I think we know how that originates. Now the question is, what about the gauge group? You know, SU3 cross SU2 cross U1. I do not know, but I have a suspicion that might come out as a generic fact. So in other words, the particular, the mass of the muon, I will be completely amazed if that's generic. I suspect that is specific to a particular rule. But the fact that the gauge group has some form, for example, the fact that the gauge group is a subgroup of E8 or something, that might be generic. It might be, how far the breaking goes by the scale we're at, that might not be generic, but something about where it lives in the space of Lie groups might be generic, which will be kind of exciting. And that, in a sense, that would be giving you sort of a core part of the standard model. Now things like the Higgs mechanism, the existence of the Higgs particle and so on, I have some ideas about how that might work. I would say too early to say for sure, but again, I think some aspects of the kind of Higgs mechanism might turn out to be generic. The problem is anytime something isn't generic, we're off doing a giant search for rules, and we haven't yet determined how difficult that is. And it might be sufficiently difficult. It may be that we'll solve it in a year. It may be that 100 years from now, that will still be a big thing to go and, you know, search for more rules and get bigger computers and try and do more, you know, can you get past 10 to the minus 1,000 seconds after the beginning of the universe type thing? Or are you stuck way back in a place where you cannot yet see the features of physics that we've been able to identify in something like the standard model?
Yes, so many of the questions that have been asked by the panel were already covered in the Q&A, but there's one that's triggered quite a lot of discussion. What experiments can we do, or what observations can we make that would help to validate or maybe even disprove your theory?
Don't know yet. I mean, I don't know yet. I hope we'll know. You know, the first step is just doing a bunch of cosmology and astrophysics, you know, on the basis of the kinds of things we've got set up. And again, best hope for a scaleless thing, maybe something about photon correlations in Kerr black holes and so on, but we don't know yet, because there's just a bunch of standard, given the model, what are the predictions of the model for specific astrophysics to work out. I mean, I feel bad because I'm talking to a bunch of obviously very practical astrophysics people who could actually take a telescope and do something. And I would love to be able to tell you what to do, but I don't yet know.
How can we get involved in this?
Well, it's maybe some people from your team would like to come to our summer school. I mean, what I think it needs to happen is, you know, what we've got to do is, you know, we've got this sort of low-level machine code theory, and we've got existing astrophysics and things, and we just got to, you know, we've somehow got to merge them together, and it's going to take work on both sides. So, for example, these oligons that I talked about, it's just standard astrophysics to try to work out what happens to particles of a certain mass in the early universe. In fact, you know, as it turns out, I wrote some paper about these things back in 1978, which I was looking at again, which is, that one happens to be about charged particles. These are certainly not charged particles. But, you know, the question of what happens to these particles when they go out of equilibrium before some kind of exponential, some infinite dimensional expansion phase, et cetera, et cetera, et cetera. It's just astrophysics in a sense. But we haven't worked it out. And that's the kind of thing that has to be worked out. And I think there's, as I say, what I'm keen on is kind of a round of brainstorming about what are the things that could conceivably be measured in, you know, the cosmic microwave background. You know, you can measure its temperature, maybe you can measure its polarization. You know, can we say something about any of those things? Is there anything else you could measure? Is there, you know, I don't know. You know, again, I mentioned the vague possibility that there might be, I mean, I think it would be very poetic if it happened that there would be essentially a sign of kind of the early, okay, the most poetic thing that could happen, but I think it's extremely unlikely, is that the first few graph updates that would happen at the very beginning of the universe would lead to density perturbations that could actually be seen in the microwave background. So in other words, that in some sense, the universe is a self-documenting place where the underlying rule visible in the first few updates would actually be something that was painted on the whole sky. It's not going to happen that way. It will be very poetic, but it's not going to happen that way. But, you know, the thing is, what can one, you know, what kinds of things, I mean, you know, I think the most interesting thing that our theory might be able to contribute quickly is new types of experiments that people haven't thought to do, and which I think this dimension change is probably one of the more obvious areas of, and so it's just thinking that through. And, you know, what does it look like if, for example, if there was an area of space-time that had different dimension, what would it do? You know, what does it do to gravitational lensing if there's some piece of, you know, space-time with different dimension? I don't know. You know, and it's not trivial to work out because we don't get to just do, you know, we don't get to write down standard differential geometry because it doesn't exist for variable dimensional space. So it's just, you know, those are really interesting things. And I'm you know, what we're trying to do, I just want to say, final sort of thing about this with this project is, you know, this is, I hope, sort of the ultimate open science project in the sense that, you know, what we've been doing, you know, we've been live streaming our sort of internal working sessions. We've been posting, sort of outrageous actually, but you know, every night when I'm working on this project, I create a bunch of Wolfram Language notebooks, and by the next morning they're posted on a public website. So, you know, they're full of terrible things that I didn't figure out and so on, but I'm sure we can look at last night's collection. You know, so we're trying to do this. And the other thing we've done is that all of the Wolfram Language tools that do all of these simulations and computations, they're all immediately available and you can run them immediately. And so, you know, I'm hoping that we will be able to get, you know, and we've seen this, by the way, and we've got a lot of very good people coming to our summer school, and we've had lots of good interactions. But, you know, we're hoping that this becomes something where, you know, we've provided some direction, but then it's kind of like, you know, lots of other people. Okay, there is a lot, in my opinion, there's a lot of low-hanging fruit to be picked in this kind of approach to physics, and we will pick only a small fraction of it, and the rest is absolutely available. And personally, I will be very excited to see other people pick some of the juicier parts of that low-hanging fruit. And we should probably stop there before your interpreter.
Yes, we should wrap up. Yes, thank you so much, Stephen. This was wonderful. I think you have shown all of us how science is being done. You know, it's an exploration every day. It's a hard business, but it should foremost be transparent to everyone on this planet.
Trying to. Seeing what happens, it's an experiment.
Exactly. Exactly. So let's keep talking.
Yes.
And I'm sure we can come up with some experiments for the future.
That will be exciting. Very exciting.
Awesome.
Right.
Thank you so much.
Nice to see
So
you.
Evelyn has some words to say.
Yep, just to finish, I just want to thank Stephen, but I want to thank for the audience for joining us today. I think the peak numbers were about 1,400. I mean, we'll confirm afterwards.
Okay.
There were many questions in the Q&A that I believe are also answered on the FAQ on Stephen's website. So you can go to wolframphysics.org/questions and you can find the answers to many of the questions. And all the talks in the series will be recorded and added to the Astrofísica UC YouTube account in the coming days with both English and Spanish subtitles, English and Spanish soundtracks. And they'll also have a higher quality resolution in case anyone suffered any internet issues and lost video during today's talk.
So we would also like to welcome everyone back again tomorrow for the final talk in this webinar series, in which Professor Didier Queloz will tell us about exoplanets, Earth twins, and the pathways for the origins of life. So please note that this talk will be at 11:15 Chilean Standard Time and not 10:30 as originally announced. And so there is nothing left to say except to thank Stephen again and the team and the panel members.
Thanks, Stephen.
And see you all very soon, hopefully.
Okay, bye-bye.
Take care, everyone.